have nice things.
Yeah? And?
No.
There we go.
Okay. All
I
right.
touched half the things like
So-
physics. What? What? Amount of word test sitting out. Stop. No.
So on thermodynamics, basically the short version of thermodynamics is that it's a study of energy transfer. Okay? And that's the easy part. The hard part is how you quantify it, how do you measure it. So here's a simple way of demonstrating this. So I've got your basic old school thermometer here, okay? And it's reading at 22 degrees Celsius, okay? So there's a bulb with a reservoir of liquid here, and it's up here to a certain point at 22. So basically what we have done as a species is that we said, hey, we're gonna put marks on a glass tube, and if that tube height, that liquid inside of there, is at a certain point, we're gonna say, that's 22 degrees, okay? So here's the three big temperature scales. You have Fahrenheit, you have Celsius, and you have Kelvin, okay? So the old running joke is Fahrenheit is what human beings feel, okay? And I can tell, like, right now, the temperature, they keep the room pretty constant at about 72 degrees. But it's odd, if that temperature creeps up to like 73 or 74, I can absolutely notice a change in you guys, because you're like, it's hot. Okay? Or if it drops to like 68, it's like, oh, it's so cold in here. Okay? So Fahrenheit, and that's the beauty of Fahrenheit. Fahrenheit in terms of divisions is the smallest of the divisions. So like a change of 71 to 72 degrees Fahrenheit is a small change compared to like a change of 71 to 72 degrees Celsius. Okay? So Fahrenheit, and they figured out that human beings have enough of an ability to notice temperature changes that Fahrenheit works for us. Okay? So Fahrenheit is what humans feel. Celsius is what water feels. So in the sense that literally if you look at the history of how they got Celsius, they took a tube like this that had no marks on it at all. It was just a blank piece of glass, no marks on it. They put that thing in water and got it to the point where the water froze. And they said, okay, where's the mark on that? And they said, it's right here. And they said, okay, we're going to make that mark 0. So at that point where water freezes, they're going to draw a line in that tube and it's going to go, that's 0. Then they're going to take that same thermometer and they're going to put it in boiling water. And that temperature where that water boils, they're going to come up here where they're going to notice, oh, the water is boiling. They're going to make a mark up there. They're going to say, that's 100. And then they're going to put 99 marks in between. That is literally how they came up with the Celsius scale. So that's why you say Celsius is what water feels. Okay? Kelvin has been said, that's what atoms feel. Okay? So Fahrenheit is what humans feel, Celsius is what water feels, and Kelvin is what atoms feel. So we're going to be working a lot more with Kelvin because that's typically what thermometers measured it. Now, here's the cool thing about thermodynamics in terms of how it works. So right now, this is at about 26 degrees, okay? So it's warmed up some, and it's warmed up some is because I was holding this in my hand. Now, as I hold this in my hand, it started off at 22 degrees, and now we've climbed all the way up to about 29 degrees. So that stuff in there, whatever the blue stuff is, okay, responds to whatever my hand is doing. Now we're all the way up to 30. So here's the question. What's the mechanism that allowed the blue stuff inside to go from an arbitrary mark of 22 all the way up to now 31?
Photons.
Photons.
Correct.
Okay.
Yes, always an answer.
It does everything. They do everything.
Photons do everything. There's some legitimacy to that.
I don't like.
So the mark went up to 31. But what did the photons do
They
as
hit,
opposed to the protons?
they hit the blue
Oh,
stuff.
yeah. They what?
They hit the blue stuff, so it moved faster.
They hit the blue stuff. Where'd the photons come from?
The
Light.
sun.
I don't think the sun's part of it. Oh, perhaps from my hand. So my hand is giving off these photons, okay, which are interacting with the blue stuff, this is the most non-scientific lecture I'm going to give you, okay? But it's interacting with the blue stuff, okay? Huh?
You give a whole lecture about cheese sandwiches. Very true.
Okay, Val,
Volleyball.
but you understood, okay?
And not the assignment.
So, the blue stuff is responding to the photons, which you can't see. You can make the argument that this is just magic, okay? What, Cohen?
Where
That's
do
what
the
the
photons in your
chemistry
hand come from?
The atoms in my hand, which came from the deaths of stars.
Where did those
So
come
it
from?
did come from
they
the
come
sun.
from the sun.
So it did come
Well,
from,
the atoms like a dead star. So,
a different sun.
that was the difference.
Okay.
So, the photons, which you can't see, are interacting with the blue stuff. So what's making the blue stuff expand?
Kinetic energy.
Kinetic energy.
Yeah.
Okay, all right. Kinetic energy is the energy of motion. But, oh, what's this?
They're moving around.
They're moving around more.
Yes.
Okay, so the blue stuff is doing more of this than this.
Extra 10.
Okay? So as they do more of this, what happens to the volume?
They go up.
Well, it goes up. Because they're going, oh, we're doing more of this, and then it takes up space. It's like second graders. If it's cold outside, like 40 degrees Fahrenheit, they tend to huddle around, right? They don't occupy much space.
Well, that starts in
You raise the temperature to 40,
It's not cold.
what's going to happen?
They're running around.
They're going to run around. They're going to occupy,
More space.
and they're getting energy from the
sun.
carried by
Photons.
photons. Okay? There you go.
We start talking
What is a photon?
So,
It's over.
well, what is a photon? Okay, that's a whole nother discussion. Photon is a bundle of energy.
There's
Okay.
Skittles.
Okay?
Pull them up.
Well, they're
Photons
Skittles.
are Skittles.
Photons are Skittles. And they come in different
Where
ways.
did these
Okay. So, one of the things that you look at when you study thermodynamics is that you can think of a measure of temperature as being like the radar gun for atoms. So if you look at that stuff being at 31 degrees, what we're saying is that those particles are moving faster at 31 than they were at 22. So the temperature tells you how fast the particles are moving. So, but that's like an average, okay? So when you measure temperature, and again, we arbitrarily put marks on a glass tube and said, hey, we're gonna call this 22, it's gonna warm up to 31. Stuff has more movement. So if you wanna quantify how much energy is in the system, and I'm guessing you all have seen this equation before, where you have Q equals M, delta T, C sub P. Okay? Now, I always have to keep track of which lecture I'm giving this in. Because it's the same equation, but physics has different units than chemistry does. So, in chemistry, that mass is going to be in grams. Now, let's talk change in temperature. Listen to me. It is not temperature. It is change in temperature. Now, how do you convert, let's say that initial temperature was 22 degrees Celsius.
Plus
Plus 273 Kelvin.
To get into Kelvin, you have 273, which gets you 295,
Yeah, that's
Hard math.
That's a yummy number.
okay? 295.
Look at that.
Let's say we go up to 30 degrees Celsius.
It's a good price.
So 30 plus 273 gets you 303,
That was hard math.
8.
okay? Now,
Changing 8.
what's the change in temperature in Celsius?
This many.
8.
8 degrees Celsius.
What's the change in Kelvin?
8 kelvins.
Also 8. So changes in temperature, whether you're in Celsius or Kelvin, is the same. Okay? Because it's change in temperature. Now, is the temperature itself different? Yes. But the changes in temperature are the same. So a 10-degree change in Celsius is the same as a 10-degree change in Kelvin. So, then you have specific heat. Remember, specific heat is measured in joules per gram degrees Celsius, which you could also write as joules because it's changed per gram Kelvin, okay, because it means the same thing. So water, for example, which is what we're going to use a lot, has a specific heat is 4.18, we'll just go with that, joules. God, this thing will not write today.
Man, if you had not dictated that, I would have had no idea what you just put down.
That's
Is that
valid.
8? Oh.
Okay, now, here's the problem with energy, okay? Is that when you all walk in, I can get an idea of how much energy you have just by watching you guys walk in, okay? And some of you have pretty consistent energy levels, okay, right? Some of you do. Chuck's pretty laid back most of the time, okay? Some of you have more variation in your energy level, okay?
Okay, what do you mean by that?
No, sometimes you're like, ah, and sometimes you're like, oh, I'm so tired. Okay?
Yeah, that's fair.
It's fair.
That's fair.
That's fair. It's not a criticism,
Fair.
it's a statement of fact,
Whatever.
okay? All right? So, but when you walk in, I can get a feel for, hey, how much energy is gonna be in the class today? So, if you think, Chuck, just shut up.
That was a very good act.
Chuck.
How's it feel?
It doesn't feel. There's no.
KCU,
KCU?
oh, CSU,
There you go.
my bad.
Cohen Charles University.
No.
No. No.
Jacob, you're not here to keep them in line, this is all on you.
What the freak, Jacob?
The father figure isn't here. Because Jake would be over there going, okay?
Jacob
Oh
just
my God.
furiously just.
If you,
furiously
Jake, if you don't
writing
watch
like,
this, we're never talking to you again.
Charles.
Okay,
Stop talking.
so, back to our story.
What was it?
So, to give you an idea of what 4.818 joules look like, okay, for those of you that haven't taken physics yet, this is a half a kilogram mass, which means that it weighs 5 newtons. It's just a number, it's 5 newtons. So if I take this and I lift it up to a height of 1 meter, I just did 5 joules of work, okay? So that kind of gives you a quantifiable idea of what a joule is. So if you look at that water, which is 4.18 joules per gram degree Celsius. So 4.18 joules would be about enough energy to lift this thing up to about this height. So if I just did that, right there, that was about 4 joules of work, okay? So that's the hard part about energy. We talk about it and all this good stuff, but we don't, it's really, really tough to quantify what that looks like. So when you look at this value of Q, and we're going to spend a lot of time talking about Q. Q is the amount of energy in the system. So all of you collectively have a certain amount of energy. If I were to add all of that energy up, that would kind of be what that Q value would be. So here's the classic example between like temperature and heat. Okay, so heat, when you look at what Q is going to be measured in. So you've got a mass that's in grams. You have a change in temperature, which is in degrees Celsius. And then you have the specific heat, which is joules per gram degrees Celsius. Those cancels out, and you have left with joules, okay? So Q is going to be measured in joules. So the classic example is that, let's say it's the middle of the winter, and you walk into your house, and the furnace has quit working, and it's really, really cold inside the house. And you have a match, okay? And you light the match. No, you're not gonna burn down the house. Let's just clarify this right now, okay? And you light the match, okay? Now, you could burn your hand with that match. If you put it near the match, boom, you're gonna burn your hand. So that match would have extremely high temperature. So temperatures, remember, is a measure of particles, okay? But so you would burn your hand, but you're not gonna warm up your house by lighting one match, okay? So you can have very high temperatures, but not a lot of thermal energy in the system. So you call the repairman comes out, hey, let me fix your furnace, boom, lights it up, okay? Now the furnace starts to work. So the air coming out of the vents might only be 80 degrees Fahrenheit. You want to warm up the house to 72. So the air coming out of the vents isn't like, oh, hey, take the paper away from the vents because the paper is going to catch on fire because the air coming out of the vents is so hot, okay? Hey, you want to cook dinner? Hey, we put a pot of water over the air vents. No, okay? The air, that system works by moving a lot of air that might be at like 80 degrees Celsius. So that's a situation where you have a lot of thermal energy in the entire system, but the temperature isn't all that high, okay? So that's the difference between Q, which is the total amount of energy in the system, and temperature, which is the measure of the individual particles. Okay, so here's what we're gonna do. So 1G, I kind of need your help with this, okay? So we're going to measure the temperature of the water, and that's going to be about 22 degrees, so I need you to hold that, okay? So right now we've measured the temperature of the water. It's about 22. What I'm going to do is I'm going to take some sodium hydroxide, and I'm going to dissolve that in the water. Okay? So, three things can happen when I put the sodium hydroxide in the water. Temperature could go up, temperature could go down, and the temperature could just stay the same. Okay? So, are we steady at about 22?
Yes.
Okay. So, I'm going to, first off, is sodium hydroxide soluble or insoluble?
Soluble.
Why?
Strong base.
Well, sodium, group 1, not all hydroxides are soluble, like magnesium hydroxide is very insoluble. But it's group 1. So here's what's going to happen, and this is going to be important in terms of the lab that you're going to do tomorrow. I'm going to take that sodium hydroxide, and if you think about it, you're going to put that on the water molecule. So here's Wally, the water molecule, right? And so the sodium obviously is bound to the hydroxide. How do you know that there's a bond between the sodium and the hydroxide?
It's solid.
It's solid. If there wasn't, guess what? Sodium hydroxide would be a gas. Okay? There's obviously a bond that holds the sodium to the hydroxide. Okay? Shocking. Now, you're going to put that in with Wally, the water molecule, right? We need to talk about what Wally's going to do. So here's the oxygen end of the water molecule. Is that positive or negatively charged?
Negative.
Negative. Oh, right. We'll get into this later. It has an extra pair of electrons out here. So the oxygen end has this dome of negativity. Okay? So that's very negatively charged. And oddly enough, the hydrogen end is positively charged, right? So you have sodium. What's the charge on the sodium?
Plus.
Plus 1. Hydroxide is?
Minus 1.
So basically what happens, the water molecule comes up and says, to the negative end, it comes up and says, yo, sodium. What do you think? So the sodium and the hydroxide have to make a decision. They go, do we stay with each other, or do we break the bond and go hang out with the water? Because that's the only way it can dissolve. The only way it can dissolve is if the bonds with water are greater than the bonds between the sodium and the hydroxide. So if the sodium hydroxide bonds were stronger, it's just like when you put that thermometer in there. Why did the thermometer stay together? The bonds are stronger, Okay? That would be really weird. It's like, it's like, hey, here's the new thermometer. It's soluble in water. Really? That's going to go well. Okay? No. Okay? How do you get it back? You evaporate the water and it reforms the thermometer. No. Okay? So you're not soluble in water. That's a cool thing, right? Otherwise, that would be awkward. It's like, you wash your hands, yeah, how can you tell? Well, part of my hands are gone. So, but there's attraction, it's just less than what holds your skin together. So, now this is the beginning of a long story.
Oh, man.
When you break bonds, that releases energy, excuse me, an input of energy. You have to put energy in to break bonds. So when you break bonds, God, this thing,
It's a song.
Oh, you're writing
break bonds.
I'm glad I know what I'm supposed to say.
That is freak.
Kiak,
Freak Bob.
The
Kiak bonus.
Okay?
the key bonds.
It's like a freak bug.
Freaky bonus.
There. So when you break bonds, that requires an input of energy. It's just like if I want to break the bonds that hold the hydrogen to the oxygen, I have to put energy into the system. But when you form bonds, oddly enough, you release energy. So this is, remember this in the lab for tomorrow. Okay? So, I'm going to take this sodium hydroxide and I'm going to put some of this in there. Now, you kind of just give this a stir. You got me?
Don't even worry.
Okay?
Are we looking at temperature?
Yep.
I was- yeah. 21 right now.
Okay, now give that a stir. And let me know what happens to the temperature.
Nothing.
Just give it time.
They do look like the little sentences in the laundry. Those look for me.
So if not,
Yeah.
we'll go for this.
I don't think it's going up. I like the sound. That is a nice sound. You know the sound.
So we were at what, 22? Now
We're
we're
at
up to like,
21.
we're at 21. We're all the way up now to like 24.
Well.
Okay.
Look who was right.
Okay?
It's increased.
So here's the point. Temperature's going up,
What?
right?
Boom. Shocking.
So the temperature is going up. So we had to have an input of energy to break the bonds, but we're seeing the temperature go up. So what does that mean?
The energy,
We're also forming bonds. So what bonds are we forming?
the water and the
Yeah, between the water. So
Ions.
there's two situations here. Okay. It costs us some energy to break the bonds because this stuff is very much dissolving. Okay. As a matter of fact, now the temperature's all the way up to like 26 degrees. So the temperature's gone up. Okay. So we've had to put an input of energy to break the bonds that hold the sodium and the hydroxide together. But then when they form the bonds, we're releasing energy. So what that tells us is that the energy released in the formation of bonds is more than the energy that put in to break the bond. So, to calculate this, I'm just going to make up some numbers. We're going to use the amount of energy that was involved. We're going to use Q equals M delta T C sub P. Now, and remember this tomorrow, and some of the problems on your assignment. When a salt or a substance dissolves into the water, that mass becomes part of the system. Now, if it had been a chunk of iron and just sat there, we wouldn't include the mass in with the water. But when something dissolves in the water, so let's say that I've got 50 grams of water and I added 5 grams of sodium hydroxide. Okay? So my total mass is gonna be 55 grams. So that mass is gonna be 55 grams. Now, we started at 21, and we are all the way up to, at this point, 28, okay? So I started at 21, the temperature went up to 28. So when you do change in temperature, and this is vital, that's going to be temperature final minus temperature initial. T minus T naught, temperature final minus temperature initial, I don't care. Okay? So let's call the change in temperature 8 degrees Celsius. The specific heat, 4.18 joules per gram degree Celsius. So somebody take, Christmas, can you do me a favor? Can you take 55 times 8 and then multiply that by 4.18?
1,839.2.
1,800, call it 1,840,
Sure.
okay? So 1,840 joules. So to make that water warm up, that would be like me taking and doing this, okay? So there's like 5 joules. So if you divided that by 5, you're gonna get about 900. No, okay, no, you get more than that. You get like about 300 and some odd times. So for me to do this, okay, about 300 some odd times would be the amount of energy that was needed to warm that up. Okay, just to kind of give you some perspective. Now, here's what's important. The temperature went up. So is this an endothermic or exothermic reaction?
Exo.
It's exothermic. Now, down here at the bottom, you have these delta H values. Delta H is change in enthalpy. Now, enthalpy is one of the most important concepts we're going to study. And there's a whole bunch of things that are very important that we're going to study. Enthalpy, entropy, gives free energy. But here's the irony of all of it. If you look at most of the things that you're going to study in thermodynamics, like for example, enthalpy, we don't have enthalpy probes. We don't have gives free energy probes. We don't have entropy probes, okay? So if you look at the big concepts that exist in thermodynamics, we don't have probes to measure hardly any of them, okay? We don't. It's like, there's no, it's like, hey, Burkamp, where's my enthalpy probe? Like, I got nothing. They don't exist. But what we do is that we measure temperature. Now, one of the key things about thermodynamics is terminology. And you have the system and you have the surroundings. So here's what happened, is that sodium hydroxide got broken apart. That's the system. The surroundings is the water. So we can't directly observe what happens when sodium breaks the bond with hydroxide. We can't do it, okay? It is physically impossible for us to observe what is happening when the sodium breaks apart from the hydroxide. But it's cool because I went from a bunch of white chunks into a clear solution and the temperature went up. So I don't know what happened. Magic! What happened to the sodium hydroxide? Don't know, it's gone, okay? Now, how can we prove that it's sodium hydroxide? What's a simple thing we could do?
Add some phenol.
Add a little phenolphthalein. Phenolphthalein, we add that too. If it turns magenta, hey, at least we know it was basic, right? So, when you look at this, we can't observe what happened. But what we do is we observe the outside effects of this, okay? So here's the good analogy. So let's say that I turn out all the lights in the room, okay? And you all are in here. And I'm going to tell you that I'm going to walk around. You can't see anything, okay? We're going to turn out all the lights. And all of a sudden you hear, bam, ah, okay? What are you going to conclude? I ran into something, okay? And then if you hear the sound of breaking glass, it's like, oh, Burkamp knocked over a glass. So you can't observe what I did because the room's dark. But by hearing and listening, you can infer what's going on. So the same thing is true of the sodium hydroxide. When the sodium hydroxide dissolves, we can't observe it. We go, oh man, but we saw the temperature go up. Cool. Now, so when you look at, and again, if you think units were important before, this is even more important. So this is the Q value. This is the amount of heat, listen to me, for the surroundings, okay? So the water is the surroundings. That would be like you all listening to what I'm doing. I'm the system, you all are the surroundings, okay? So to observe what I'm doing, I look at the reaction of the surroundings. I can't observe what's happening with the sodium hydroxide, but I observe what happens with the water, because that's something I can measure. Oh, the temperature of the water went up. Water molecules somehow, through magic photons, got more energy, okay? Now, don't beat yourself up and go, oh, right, how do they have more energy? Do they have like little gas pedals that they push down? How do they move faster? Because it looks like water, okay? Don't know what's happening. But here's what did happen. The blue stuff gained energy. How? Just like it did from my hand. By
The sun.
Photons.
photons, okay? Because something made the blue stuff move faster. So the little particles are bouncing on it, and here's, if you think about it, so here was the bulb at the bottom, and there's the blue stuff. So basically what happened is that the water started colliding more with the outside of the thermometer. The stuff inside goes, ooh, this is bad, okay? It got agitated. And it said, ooh, I got bad, right? So they got agitated. They started doing this, right? Happy hands, right? Or what is it with choir? Is it happy hands?
Jazz hands.
Jazz hands, jazz hands. My bad. Jazz hands. Okay? So the water molecules started doing jazz hands, right? And when they do jazz hands, you have to occupy
More space.
more space. So the water molecules getting jazz hands, right? So they're going, ooh, gotta have more space. Wow! And so they went up. So the energy got transferred from the water through the glass wall into the blue stuff. The blue stuff got jazz hands and occupied more space, and it went up in the column. Okay? So something looks fairly rudimentary actually is fairly complex if you think about it.
It got warmer.
Now, enthalpy
It got warmer.
is shown by delta H, okay?
I just don't think you're saying entropy, but like it is.
Yeah, no, it's enthalpy, no. No, entropy is disorder. My room is disorder, okay? This is enthalpy, okay?
It sounds like you're saying entropy with a lisp though.
I know, I'm not.
Are you
Maybe
sure?
that's how it got started, I'm not sure. Don't know the origins. But here's what's important. This is in joules per mole. Okay, now we have to introduce the mole. Right. Now, so down here, the bottom, on these lecture notes, one of the things you have to begin to understand and memorize without exception is if delta H is positive, that's an endothermic reaction. If delta H is negative, that's an exothermic reaction. If you're into flashcards, make flashcards. Oh, endothermic reaction, negative delta H, positive delta H. That is something you have to know without hesitation. Now, but this is for the system. But you're going, Burkham, we don't have the system. Yeah, you're right, we don't. Did the water gain energy?
Yes.
Miss Sut, can we see little jazz hands?
For what?
Just do it. Just jazz hands.
Like, are we talking like,
Yeah.
That's
Yeah.
good.
or do you want high V jazz hands?
We need, this is relative scale, the water went from 22 to 28.
6 degrees?
Yeah. So how much, so we need a relative scale on jazz hands.
How much water? How many mLs is that?
About 50.
So 50 times 4, 200 times another 8 degree, or 6 degrees, you said?
Mm-hmm.
1200?
Yeah, give or take.
Let's see, we're doing, this is like I'd say like here.
Okay, all right, nice. Okay. Now, imagine that we have a thermometer full of that. What's going to happen to the space?
It's gonna go up.
Oh, it's going to go up. Oh, okay.
Try to get jazz here.
Now, that's the system. What we're worried about is the surroundings, because that's what we can observe. So, here's the absolute golden rule. Energy has to be conserved. So, if you think about it, the energy to make the blue stuff get jazz hands had to come from somewhere. Where did it come from?
Water.
Oh,
Breaking of the bonds.
oh, the breaking of the bonds, and then
The making.
the breaking of the bonds, and then the
Yes.
forming of the bonds,
Yes.
right?
Yeah.
So, the breaking of the bonds reduces the amount of jazz hands, but the formation of bonds makes more jazz hands.
So you're saying because we can't stick a thermometer inside of the bonds, we gotta use Q solution? And then concentration of energy means that Q reaction is the same magnitude but the other sign? Crazy!
Crazy!
So my solution gained 1800 joules? That means my reaction lost 1800 joules?
Shocking.
Crazy!
No, that's magic.
Oh,
No,
Or it's just magic.
I'm just stealing stuff from you to test their airbags. We're doing gas laws.
we are in dark magic.
What year does AP come about? Like,
This is
Their
this is
airbags suck. I'm gonna pop them.
I have no idea.
no.
I remember that.
I remember that a lot, but no, we're just moving past.
Okay, anyway, back to jazz hands. Back to jazz hands. So, this is for the surroundings. So here's the golden rule. Whatever energy is lost has to equal the energy that is gained. No exceptions, okay? So, if the surroundings gained 1,840 joules of energy, that means the sodium hydroxide as the system had to lose that amount, right? So, here's how you're going to calculate delta H. It's exactly what Mrs. Z said. You're going to have opposite signs, okay? So, if the surroundings are positive, that means the system is going to be
Negative.
so to do this, I'm going to take, so what I want to try to figure out is what's the value of delta H for this, what's called the dissolution, which is a technical name for dissolving, okay? For the dissolution of sodium hydroxide. So, I got my delta H, and that I'm going to make that a negative 1840. I'm going to switch the sign, okay? Because I'm worried about the sodium hydroxide. I'm not worried about the water, I'm worried about the sodium hydroxide. Now, I have to divide it by the number of moles of sodium hydroxide. So let's say that I had, for the sake of argument, 5 grams of sodium hydroxide. Well, what's the molar mass of sodium hydroxide?
some.
40.
Oh.
Right, I was thinking
Yeah,
sodium.
I just knew that.
Well, sodium is 23, oxygen is 16, hydrogen is 1. It's easy. So hydroxide is 17, sodium is 23. 40.
I don't have the fingers to do that one, so
I just walk.
Rude.
I ran out.
I just walk around.
Rude.
So everybody would know it's the.
Okay, do you know how many times?
Well, you expected us to also know that.
We're just babies.
Okay, so somebody take 5 and divide it by 40, and then take 1840 and divide that by that.
Good year.
Or take 1840 times 5 and, or times 40 and then divide that by
14,713.6.
14,700 what?
13.6.
Yeah.
Now, typically, because these are big numbers, we work in kilojoules. Now, you divide that by 1,000, you get like 14.7 kilojoules per mole.
5 divided by 40, and then 1,800 divided by that number.
Now,
I used exact values.
We have 5 grams, and it's 40.
it is. Oh, now, this has to be negative. Why?
Because it's negative.
Because we switched the sign because we're worried about the system not the surrounding. So we look at what happens with the surroundings, and then we figure out what happened with the system.
Exothermic.
Ah, it's exothermic!
Yes.
Wow! Woo! Because jazz hands went out. Okay?
Just hits
There you go. Now, that's the thermo side of it. You could also involve gases. So, oh yeah. So on the back side over here, okay, on the back, we have, what? Sorry, it's just that small. Okay?
I know that.
Now, that's W. So, for those of you that haven't had physics yet, the W stands for work. So here's a very short version of work. To do work, you have to exert a force over a distance. Okay? Short version of work. So here's the classic example. So I'm going to take this. Pull that out.
Go ahead and name it. See how far you can go. See how high up.
Take a little bit of cotton.
Momentum stays the same.
You have
velocity
those,
stays the
you
same.
have those little wires at that in-degree angle, and your depth node is just the full of the math done out, and you see it lines out. The last experiment.
Yeah.
Greg, you taught me so much.
Come on.
I looked away for 1 second.
Okay. So, when I compress this cylinder like this, am I doing work? Yes, why? Force over distance, right? So what am I doing to the Timmies inside the cylinder? Compressing them. Now, they don't like to be compressed, okay? And you can tell that why.
Pushes back up.
Because when I let go of it, if they liked being compressed and I let go of it, what would they do? They would stay there, right? Now, so work, and this gets, again, there's chemistry version of this is different than the physics version of this. It's still negative P delta V, okay? Now, in a chemistry setting, pressure is typically measured in atmospheres, okay? So ATM. So right now under normal atmospheric pressure, you guys are under about 1 atmospheric pressure. Now, this is going to be changed in volume, which is final minus initial, or V minus V naught.
Oh, work.
Work. Oh.
Work.
Work.
That's what I said.
Hey! Do you have like a 5 pound, like a weight? You know what I'm saying? Like a
I
plate?
got a bowling ball right there.
No, but it won't sit on this. So look, I did some ideal gas law. Find volume of this baggie.
Yeah.
How much carbon dioxide they need in moles converted to their reactants
Okay.
so that they can inflate this.
Yeah.
But I think this is too light. I feel like I'm not pushing them hard enough if this is just not heavy enough. But I don't think a bowling ball will sit on it. Do you have like
No.
a plate, like a 5 pound weight?
This is not a weights class.
Somewhere in the back, somewhere in there, there's like a big piece of metal, like about this big, that's about
Although
an
you
inch
have
thick.
Kevin might have.
Somewhere back there.
You.
I don't know where.
In your closet?
No, like out here. Oh, there's a big chunk of
See what I
concrete.
have in here.
Bet.
That's what I
There you go. Okay, now, here's what's gonna be important, is sign. This is all about the sign. So, when I compress this down, is my final volume bigger or smaller than my initial volume?
Smaller.
Smaller. So, if my final volume is less than my initial volume,
That was good.
okay,
Wow.
right?
Oh, that's a.
And there's a negative sign out there, my V minus V naught will have a,
Negative value.
Or that'll be negative.
the
But
V
then
naught
they work.
minus, V minus V naught will be,
Negative.
but then I'm gonna multiply that by,
Negative pressure.
so
Which
work
makes
is
it
going to be
Positive.
positive. Okay. Now, this is where this gets weird in terms of units. In a chemistry class, the volume is going to be measured in liters. So, in
This is pink.
a chemistry class, work is in atmosphere liters. But here's the problem,
It's that.
okay?
Let's make this easy.
The Q value, the thermal part of it is going to be measured in joules.
Everyone's
Joule
favorite
atmosphere
unit,
liter.
joule atmosphere.
I can't take joules and add it to atmosphere liters. So over here, on the back side, I have this handy dandy little conversion. That one atmosphere liter is 101.3 joules.
Okay, where does that come from?
The what?
It's just a standard conversion.
No, let's.
No, that is not standard.
Yeah,
That can't, what?
Once we get into gas laws, I'll show you where the number comes from, okay?
That's a unit from now on. That will help me.
No, it's not. Just accept it, okay? Because I gotta get through this stuff and then we'll talk about it
This is
tomorrow.
magic.
Sounds good.
Okay, so here's the deal. So
I get a question.
and this is important in terms of sign, if the volume gets smaller, work is done on the gas. If the volume gets bigger, work is done by the gas. Now, if I do this very rapidly, we'll push this down very rapidly, okay? So when I do this very rapidly, what you should see, hopefully, is that the cotton caught on fire, okay? So what happened is that there was no actual fire, there was no match. But what happened is that I greatly increased that pressure so rapidly that the internal energy went up so much that it ignited the cotton that was inside of it, okay? Now, obviously time is a factor. If I do that slowly, nothing happens. But if I do it very rapidly, because I don't give time for the photons to escape, and the photons stay in there, they find the cotton and go, I'm smoking hot, and I'm going to make the cotton catch on fire. What?
Is that like a momentum thing, or?
No, really not momentum. This is photons.
Wait, is
It's all about photons.
So how is
How are they still here?
Why does
Okay. I know
What
it
is
may
going
sound,
on?
you gotta go. Let me hand out the assignment.
accelerate photons?
What is
What is happening?
What do you mean assignment?